In this part of the Neurocomputers and Deep Learning course related to training feedforward neural networks, you will learn Perceptron Convergence algorithm for training a single neuron, which is called Perceptron. The method of storing and recalling information and experiences in the brain is not fully understood. However, experimental research has enabled some understanding of how neurons appear to gradually modify their characteristics because of exposure to particular stimuli. The most obvious changes have been observed to occur in the electrical and chemical properties of synaptic junctions. For example, the quantity of chemical transmitter released into the synaptic cleft is increased or reduced, or the response of the postsynaptic neuron to receive transmitter molecules is altered. The overall effect is to modify the significance of nerve impulses reaching that synaptic junction on determining whether the accumulated inputs to postsynaptic neuron will exceed the threshold value and cause it to fire. Thus, learning appears to effectively modify the weighting that particular input has with respect to the other inputs to a neuron. In this chapter, learning in feedforward neural networks will be considered. First, we will consider perceptron convergence procedure. Perceptron was introduced by Frank Rosenblatt in the late 1950s with a learning algorithm on it. Perceptron may have continuous valued inputs. It works in the same way as the formal artificial neuron defined previously. Its activation is determined by equation. Activation is weight transpose U plus theta. Moreover, its output function is output function f applied on activation is equal to +1 for activation greater equal to 0, -1 for activation less than 0. So the output is having value either +1 or -1. A perceptron is given in this figure. We have connections from 1 up to n together with connection weights. Theta is the threshold. It is connected to input 0, which is 1. Here the output function is the sine function. Now consider such a perceptron in n-dimensional space. The equation weight transpose u plus theta is equal to 0. That is W1 multiplied by U1 plus W2 multiplied by U2 and up to Wn multiplied by Un plus theta multiplied by 1 is theta. So here plus theta is equal to 0. Defines a hyperplane. This hyperplane divides the input space into two parts such that at one side the perceptron has output value +1 and in the other side it is -1. If the input space is two-dimensional, then it becomes a line dividing the plane into two parts. If it is three-dimensional, so the hyperplane is a plane. However, for the input spaces having dimension larger than 3, we are calling them as hyperplane. A perceptron can be used to decide whether an input vector belongs to one of the two classes, say classes A and B. The decision rule may be set as to respond as class A if the output is +1 and as class B if the output is -1. The perceptron forms two decision regions separated by the hyperplane. The equation of the boundary hyperplane depends on the connection weights and threshold. Example 1. When the input space is two-dimensional, then the equation W1U1 plus W2U2 plus theta equal to 0 defines a line as shown in the figure. Perceptron output defines a hyperplane that divides input space into two separate subspaces. This is the line equation defined by the perceptron output when it is set to 0. Here we have two-dimensional input space, so the hyperplane is a line. This line divides the space of input variables u1 and u2, which is a plane, into two separate parts. This is the plane of input variables u1 and u2. So this line is separating this plane into two parts. In the given figure, the elements of the classes A and B lies on the different sides of the line. Connection weights and the threshold in a perceptron can be fixed or adapted by using a number of different algorithms. The original perceptron convergence procedure, developed by Rosenblatt in 1959, for adjusting weights is provided in the following. This is the perceptron convergence procedure. Step 1. Initialize weights and threshold. Set each wj 0 for j starting from 0 up to n in w0. This is the vector made of wj from 0 up to n to small random values. Here w initialize weights and threshold. Set each wj0 for j from 0 up to n in w0 to small values, where w equal to wt is the weight vector at iteration time t, and the component w0 here is equal to theta, corresponds to bias or threshold. Step 2. Present new input and desired output. Present new continuous valued input vector uk along with the desired output yk, such that yk is +1 if input is from class A and -1 if input is from class B. Step 3. Calculate actual output. Actual output xk is equal to the output function f applied on activation, which is weight vector transpose multiplied by the input vector. Step 4. Adapt weights. Weight at t plus 1 is equal to weight at time t plus eta multiplied by yk minus xk at time t multiplied by input k. Here notice that w is a vector of dimension n+1, and also u is a vector of dimension n+1. All the others here are scalar values. Eta output and actual output are scalar values, where eta is a positive gain fraction less than 1. This is also called learning rate. Step 5. Repeat steps 2 to 4, these steps, until no error occurs. Example 2. The figure at right demonstrates how the line defined by the perceptron's parameters is shifted in time as the weights are updated. At time 0, suppose that this is the initial line. It is determined by W1, W2, and theta, which are initialized randomly. Then, due to the errors in the classification, W1, W2, and theta are updated such that it is shifting and turning its direction, and it goes on in this manner until W1, W2, and theta are adjusted by the convergence procedure such that the classes A and B lies at opposite sides of the line defined by the perceptron. Although it is not able to separate the classes A and B with the initial weights assigned at time t equal to 0, it manages to separate them at the end. In Rosenblatt 1959, it is proved that if the inputs presented from the two classes are linearly separable, that is, if they fall on opposite sides of some hyperplane, then the perceptron convergence procedure always converges in time. Furthermore, it positions the final decision hyperplane such that it separates the samples of class A from those of class B. One problem with the perceptron convergence procedure is that decision boundary may oscillate continuously when the distributions overlap or the classes are not linearly separable. In this figure, in the left one, we have overlapping distributions for the class A and B, and this one shows a non-linearly separable distribution. There is no line to separate these two classes. In both cases, perceptron convergence algorithm will not converge. Here we have types of regions that can be formed by single and multi-layer perceptrons. Here we have a single perceptron. We are in two-dimensional space, so we have connections to U1 and U2. And suppose that we have also threshold here. By using a single perceptron, a line is defined and it separates the space into two parts. This is the exclusive OR problem. In the space we have 4 points. This is corresponding to 0, 0, 1, 0, 0, 1, and 1, 1. The output is 1 for these 2 points, and it is 0 for these 2 points. By using a single perceptron, it is not possible to separate the points for which the output is 0 from the points for which the output is 1. In most general case, we have such a line in two-dimensional space, which becomes a hyperplane in higher dimensional input spaces, and it is only separating the input space into two parts. If we are using two levels of perceptrons, suppose that this is corresponding to an AND gate, and all these perceptrons in the first layer, in the hidden layer, are defining a line, and suppose that this is defining this line and that one defining that line, and if we use AND gate, it finds the intersection of the regions defined by this perceptron and this one. So if we are allowed to use two-level perceptrons, if we are allowed to use two-level perceptrons, then we are able to solve the exclusive OR problem. In general, the number of perceptrons here defines the number of lines, and this perceptron is to take the intersection of two regions. So such a convex region can be defined by two-layer perceptron. And if we have one more layer, then the neurons in the first hidden layer is showing the number of lines defined here, and the neurons in this layer are AND gates and AND in the line, so we can define such a convex region with one of the perceptron in this layer, and also here there is another perceptron to take the intersection of the regions defined by these lines, And then here, by addition of one another neuron, which is an OR gate, we can find the union of the regions. So, with such a structure, also exclusive OR problem can be solved. But notice that 2-level is enough, but it can be solved also 3-level perceptron. In general, it is union of convex regions. It may be such a region as given here. You may divide this into convex regions, and this is union of them.